For a given function in terms of T1 and T2, we have to find whether this function is an autocorrelation function or not. The given function is min of T1 and T2. To find out whether it's an autocorrelation function or not, we'll have to prove if it has a positive definite or not. For example, if we have a series of points which ranges from T1 through Tn, where we have a condition that T1 is less than T2 is less than T3 and so on up till Tn, then what will be the autocorrelation matrix? Every term Rij would be Ti, where Ti is less than Tj. So in this case, R can be written as this expected value of xt1 into x T2 conjugate. Now we'll have to show that whether this expected value is a positive definite or not. To prove that, we take a scalar matrix, and it can be real or complex, and then we take A conjugate RA, and we have to prove that if this product is a positive number, positive definite, then this function is an autocorrelation function. So for that, we have A conjugate xt1, xt2 conjugate into A. Now we can see that this, if we consider this as y, then this is y conjugate, and in other words, we can say that their product would be the square of magnitude, and the expected value of a positive number would always be a positive number which is greater than 0. So we can say that R is a definite, positive definite. Now for the given function, we have the following matrix. This was the generic rule to find autocorrelation function. Now for this given function, we have this kind of a matrix in which first row and first column are T1, and then from A22 onwards we have T2, and similarly here we have T2 up till Tn. Now to prove that this is a positive definite, we just take T1 out of the matrix such that we have a matrix of all T1s, and the rest is first column and first row would be 0, and the other element, and from other elements we'll be subtracting T2 from each element. Now for the first part, we can write it as T1, taking T1 as common. The matrix left would be a matrix containing ones only, which can be written as a column vector into a row vector containing ones only. Similarly, from the second part, we can take T2 minus T1 in common. This term is found as we had T3 minus T1 here, and we subtracted T2 minus T1 from this term. So we are left with actually T3 minus T2. Similarly, the same pattern will be followed throughout the matrix, and we will get the whole matrix would be T2 minus T1 would be subtracted from the whole matrix. Similarly, following the same pattern, we can take T2 minus T1 common and write the other matrix in terms of a